Okay, let's get started. Happy birthday to whoever's birthday it is, although I suspect it's a hoax at this point. So either there's a lot of birthdays or someone really likes milking their birthday for a long time. So, all right, so we're gonna move on to finish most of what's technically in chapter 7. We're gonna finish today. There is another section that we cut out of chapter 3 that's sort of related to this stuff that we'll cover next time. So we're kind of getting finished with this part of it. And then the exam, of course, is finishing up today. So I guess all of you have probably taken it because you're here right now. And we'll get the results for that on Monday, sort of on a whole. And if you want to go over your individual results, they should be available sometime tonight in Blackboard. Probably around 8 p.m. is, I think, when we usually release them. And if you want to talk to me about your exam, of course, you can make an appointment or come stop by my office whenever I'm there. All right, so today we're going to talk about a concept called Hess's law first. And what this sort of stems from is what we ended with last time. So as we talked about last time, we can sometimes have sequences of chemical reactions where we have two or more chemical equations, and we can combine them into one by adding the reactants on one side of the arrow, the products on the other side of the arrow, and then anything that appears on both sides would cancel out as what we call an intermediate. So that's what we did at the very end of last time, and it may not have been clear why this was relevant to enthalpy and the things that we're talking about in chapter 7, but this is what we're going to get into now at the start of today. So let's just finish with one last example of how we can add together two chemical equations. So let's say we want to prepare the compound phosphorus oxychloride, POCl3, and we can do it in two steps. So let's say the first step takes elemental phosphorus, which has the formula P4, chlorine, and we make PCl5. So that's going to be the first step of our chemical reaction sequence. Is going to be to combine phosphorus and chlorine to make PCl5. So that's one chemical equation. We need to make sure it's balanced. And so we have 4 phosphoruses on the reactant side, so we're going to put a coefficient of 4 there on the products, and then we need to have 5 Cl2s to balance chlorine. So that's the first balanced chemical equation, the combination of P4 with Cl2. And then the second step we're saying is we're going to take that PCl5 and we're going to hydrolyze it, react it with water to form the POCl3 and HCl. I'm sorry? Yeah? Yeah, because I can't do math today. I guess I'm checked out because it's my birthday or something. It's not actually. So, all right. So we have PCl5 and water going to POCl3 and HCl. And so if we want to balance this step, all we have to do to balance this one is put a 2 in front of HCl. So we get chlorine's balanced by doing that, and then everything else is already worked out. So that's the second chemical equation, the hydrolysis of PCl5. We want to combine these two into one, as we're saying, to get the overall reaction. And so what we notice is when we want to add together two chemical equations, we have to look at what I'll draw that later. We look at what the intermediates are. So we have PCl5, which is formed in the first reaction and then used as a reactant in the second one. We want that to cancel out. So we have to modify the coefficients to make sure that the intermediate cancels out. We're forming 4 PCl5s. We're only using 1. So what we're going to do is we're going to take every coefficient in this equation and multiply it by 4. So we're going to get this modified form of the second equation where we take every coefficient and multiply by 4. We can't just do it to one of the coefficients because that will unbalance the reaction. So we need to do it for every single one. And then what we're going to do is we're going to combine this first equation with this modified second equation. And so what we see now is that on the reactant side we have P4, so everything that's on the left side of the arrow we just add together. P4 plus 10 Cl2 from the first equation, and then from the second equation we have 4 PCl5, but we know that that's going to be an intermediate that cancels out with the product on the other side, so that's not going to appear in our overall equation. And then we have 4 H2Os left over. And then on the product side, from the first equation we had 4 PCl5, but that's our intermediate, which cancels with the 4 PCl5 that's a reactant in the second one. and all that's left then is 4POCl3 plus 8HCl. So I kind of combined two steps into one here. Before, what we did last time was just add together all the reactants and products, cancel out what appears on both sides. Here I sort of skipped that intermediate step and saw that by modifying the second equation, the PCl5 cancels out, so we can just write everything else when we add the two equations together. All right, so that's kind of how we're going to do this. Is, we need to be able to modify coefficients, and in some cases flip a reaction to be able to add it together correctly. So that's kind of the deal that we're going to use then in determining delta H for some chemical reactions. So let's now talk about then the properties of delta H, because what we're going to be doing with this, our ability to add reactions and add equations together, is we're going to be calculating delta H for a reaction. If we know delta H is for two other reactions and we combine them, we can calculate delta H for the combined reaction. And this is often how we do it because it's a bit labor intensive to go into the lab and measure delta H every time we want to do it. So if we know delta H for two other equations that we can combine to make whatever equation we're interested in, we can calculate delta H. So to be able to do that, we need to know what are the properties of delta H and how they change whenever we change coefficients in an equation or add two equations together. So let's talk about that before we go into the details of how this works. So the first thing, we've already learned about the sign of delta H. It can be positive or negative, and that is dependent on whether the reaction is endothermic or exothermic. So exothermic reactions have negative delta H's, endothermic reactions have positive delta H's, and both are certainly possible. So that's the sign of delta H. And then the magnitude of delta H, we kind of saw this when we were doing calorimetry problems. Delta H is, again, the amount of heat that's involved in the reaction at constant pressure, and how big the sign of delta, or how large delta H is proportional to the amount of substance that we use. So this is what we refer to as a thermochemical equation. So let's say we have a chemical equation with its associated delta H. So the one I'll talk about is which will come up later on, is the decomposition of water to make its elements, hydrogen and oxygen. So let's say we have the equation written as this, where we're decomposing 1 mole of water, which gives us H2 and 1/2 O2. And the delta H for this process is 286 kilojoules. So when you see it written like this, what this means is that for every 1 mole of water we decompose to make 1 mole of hydrogen and 1/2 mole of O2, that there's going to be 286 kilojoules of heat that need to go into that. So it requires 286 kilojoules to decompose 1 mole of water into its elements. So that's what this chemical equation says. Now, the point I'm going to make here is that this value of 286 kilojoules applies specifically to when we're producing 1 mole of hydrogen, or alternatively decomposing 1 mole of water. But then the other thing, now let's think about what happens instead. Let's say we're producing 2 moles of hydrogen. How much heat would be required for that process? Do we think it'd be larger or smaller than 1 mole? It should require more heat to produce more hydrogen. And the way we can do that then is that delta H is going to be, if we have 2 moles of hydrogen, we know from the balanced chemical equation that it requires 286 kilojoules, 6 kilojoules per 1 mole of H2, because hydrogen has a coefficient of 1 in the balanced equation that I gave you. And so we just have to double the delta H to get 572 kilojoules. So if we're going to produce 2 moles of hydrogen, it requires twice as much heat. And there's going to potentially be some problems on the next homework assignment and exam that'll ask you to do this sort of analysis. If we know delta H for a chemical equation, which is in terms of moles of substance, what would be the delta H if we had a sort of a different scale for that reaction, or a different amount of substance involved besides 1 mole as we have here. So that's how we can kind of use delta H, and we can say then that the amount of heat that's either absorbed or released by a chemical reaction depends on the scale of the reaction, depends on how many moles of substance are involved, and at least that should be, I think, intuitively pretty reasonable. So that's kind of some properties of delta H. Now let's look more specifically then at how delta H changes when we either change or combine chemical equations. So let's say we reverse a chemical equation. So we know that delta H is equal to the enthalpy of the products minus reactants. It's always final minus initial. In a chemical reaction, the final state is your products. The initial state is your reactants. So that's kind of the definition of delta H. So if we have a chemical equation, let's say magnesium carbonate decomposing to magnesium oxide and carbon dioxide, delta H for this reaction is positive 117 kilojoules. Now what do we think would happen if we wrote the reverse equation? So we took the reactant, so the products from this equation become the reactants, and we're considering then magnesium oxide combining with CO2 to make magnesium carbonate. So we're doing the exact opposite chemical reaction down here. The products become the reactants become the products. And so what would delta H for this be? Any guesses? It's just going to be the negative of this, minus 117 kilojoules. So if we reverse a reaction, if we flip the reactants and the products, delta H changes sign. And that comes from the definition that I gave you, which is that delta H is the enthalpy of the products minus reactants. If we flip the order, reactants minus products becomes the new expression, and then delta H just changes sign. So anytime we flip a chemical equation, all we do to delta H is just change the sign. We don't change the magnitude of delta H. Okay, so that's one thing we'll want to be aware of. And then what happens if we change the coefficients? As we kind of already saw, delta H is going to scale by the same amount as the coefficients. Alright, so let's say we want to consider this equation here. 2 magnesium carbonate. Now, this isn't going to be written with lowest whole numbers, but let's say we're adding 2 equations together. We need to double the coefficients for this one. So this chemical equation is 2 times this one up here. So we took this equation and just doubled all the coefficients. And then delta H would also be doubled then. So the original delta H was 117. We've doubled the coefficients. So then delta H becomes 2 times that. Okay, so if we double the coefficients, delta H doubles. If we quadruple them, delta H quadruples. We can also do fractional coefficients. So if we had, instead of 1/2 magnesium carbonate going to 1/2 magnesium oxide plus 1/2 CO2, what we've done here is we've taken the coefficients and we've divided them by 2, or halved them. And so the delta H would just be 1/2 of its original value of 117. Alright, so when we change the coefficients in a chemical equation, the delta H scales by the same amount that we change the coefficients. And as we've already emphasized, if you're going to change coefficients in a chemical equation, you have to do the same thing to all of them. If you multiply one coefficient by 2, you have to multiply all of them by 2 to keep the equation balanced. And then delta H would then scale by that same amount. So that's kind of what happens. And then finally, the last thing we need to talk about before moving into Hess's law, which is what this law is all about, is what happens to delta H when we add together chemical equations. And it's pretty simple in this case because the delta H's are also additive. So if we have our total delta H, which is, if we have a reaction that's a sum of 2 or more other reactions, the total delta H is just going to be the sum of all the individual delta H's from the chemical equations we're adding together. So if we know delta H for all of the equations we're adding together, the delta H for that overall combined equation is going to be just the sum of all 3 of those. So as an example of this, let's say we're adding 2 equations. So let's take that one that we just did, magnesium carbonate, to go to magnesium oxide plus CO2. And we saw that delta H is 117 kilojoules for this. And then let's say we want to combine this with the second equation where the CO2 that we form, we're going to hydrogenate it to form methanol. So H2 plus CO2 going to CH4O and water. So let's say this is the second equation we're considering. You need to put a 3 there to balance it. Delta H for this is minus 131 kilojoules. So then our overall equation, when we add these two together, we have CO2 is an intermediate. It's formed in the first equation, consumed in the second equation. So when we add them together, the reactants that are left are going to be magnesium carbonate plus hydrogen, 3 H2s from the second equation. And then on the product side, what's left is magnesium oxide, CH4O, which is methanol, and then water. So that's our combined chemical equation. And then the delta H for this combined equation is going to be just the sum of the delta H for the first equation, which I'll call delta H1, plus delta H for the second equation, delta H2, which is 117 kilojoules, plus negative 131 kilojoules. We don't change any signs here, we're just adding them together directly, or minus 14 kilojoules. Alright, so what Hess's law allows us to do is, if we wanted to find the delta H for the reaction of magnesium carbonate with hydrogen to form magnesium oxide, methanol, and water, if we want to find the delta H for that process, and we know the delta H for these two, which we add together to get that, we can just add together the delta H's. So it allows us to take potentially simpler chemical equations, combine them in different ways, and then allow us to determine delta H from the combination of those. Alright, so any questions on those concepts before we start doing some examples? So the way that we're going to typically see Hess's law on homework and exam questions is we're going to give you a chemical equation, let's say in this case the dimerization of NO2 to make N2O4, and then we're going to give you 2 or more, usually no more than 3, we'll try to not be too evil to you. So we'll give you 2 or 3 other chemical equations where you have to figure out how to combine these 2 equations to figure out what delta H is for the unknown chemical equation, the one that has the unknown delta H. Alright, so that's what your job is going to be. It's a little bit like putting a puzzle together, because you have to figure out how to first add together the chemical equations, then you have to determine what happens to delta H when we combine those 2 equations in different ways. So we have our overall reactions given up here, as I said, dimerization of NO2, and we have 2 individual equations that we need to figure out how to add together to get our overall equation. So the way that you want to do this is there's going to be some species that appear in both equations, right? So if we look at this, we see that nitrogen appears in both, although it's not in our overall equation. Oxygen appears in both equations. But we see that NO2, which is the reactant in our overall chemical equation that we're trying to find, appears only here in the first equation, but it's a product. So we want to have 2 NO2s on the reactant side of our overall equation once we add them together. So what we're going to do is we're going to take this first equation, we're going to flip it, and we're going to multiply it by 2. Okay? So if we flip this and multiply it by 2, we're now going to have 2 NO2s on the reactant side, which is what we want when we add the 2 together. Okay? So we take the first equation, we flip it and double it, and that gives us 2 NO2s. So when we flip the equation, we take the products and make them reactants. Reactants become products, and then we multiply every coefficient by 2. So by doing that to the first equation, we get 2 NO2 going to N2 plus 2O2. And then what the delta H becomes is just minus 2 times that first delta H. Okay? Because remember, we flipped the equation, so that's going to change the sign of delta H, and we double the coefficients, so that's going to double the magnitude of delta H. We're doing 2 things here. We're flipping and doubling. So our delta H gets multiplied by negative 2, and that becomes minus 68 kilojoules. All right, so it's hard to look too far ahead. We don't know how this is going to necessarily combine with the second one, but we see that what we have now is an equation that has 2 NO2s on the reactant side, which is what we want for our overall equation. Now we have to look at the other species, which is N2O4, And we see that N2O4 appears as a product in the second equation, and it already has a coefficient of 1, so we're not going to do anything to N2O4. We're going to take the second equation as is given to us, N2 plus 2 O2s going to N2O4. Delta H is unmodified, it's the same equation, so same delta H. And then what we see is when we combine these two together, we're going to have N2 formed in the first equation that gets canceled out in the second equation as a reactant. 2 O2s forms in the first and gets canceled out in the second. And that leaves us with the equation we want, 2NO2 going to N2O4. Alright, so that's how we can combine these two equations to get the overall chemical equation we're interested in. And then to find the delta H, it's going to be negative 2 times delta H1 plus delta H2, which as we said is negative 68 kilojoules plus positive 10 kilojoules, and that comes out to minus 58 kilojoules. Alright, so that's the delta H for the dimerization of NO2, which we can determine using these two known chemical equations. Alright, so as I said, the strategy here is to find reactants or products in your overall chemical equation that only appear once in the equations that we give you. And then you're going to modify these equations in such a way as to put the correct species on the correct side of the arrow and with the correct coefficients. So it becomes a little bit like putting a puzzle together. And if you trust yourself to do that correctly, then you can be pretty confident that the intermediates that are involved, which don't appear in your overall equation, that those are going to cancel each other out at the end. All right, so that's an example with 2 equations. Let's do a couple with 3 equations, which is as complex as we'll get. So let's say we want to do this one. We're determining delta H for the formation of C2H2 from carbon and hydrogen. And then the equations we're giving you are these ones down here. So the combustion of C2H2, the formation of CO2, the formation of water from hydrogen and oxygen. Those are the 3 chemical equations. We want to figure out how to add them together to get this overall this overall equation so we can determine its delta H. Alright, so again I'm going to number the equations so we can keep track of them easier, 1, 2, and 3. And we don't necessarily have to go in order when we start combining them, but let's look at what we have here. So our overall chemical equation has C2H2 as a product, 1 C2H2, a coefficient of 1. And if you look here at the given equations, C2H2 only appears in the first equation, but it's on the reactant side. We want it to be on the product side, so what we're going to do is we're going to flip that first equation. Take the negative of it, the inverse of it. And so this first equation then we're going to have 2CO2 plus water. Sounds like it's raining. Perfect. We're all stuck in here anyway, so what's the big deal? So that's going to be the inverse of the first equation, or flipping it over, flipping the reactants and products. And that means then the delta H of this is just going to be the negative of that first delta H, or positive 1299.5 kilojoules. Alright, so we flip the first equation, and we also then have to flip the sign of delta H. That puts C2H2 on the product side, which is where we want it in our overall chemical equation up here. Then we look at the second equation. We see that we have carbon is a reactant in our overall chemical equation. It only appears in this second one here. We have a coefficient of 2 in the chemical equation we want. This one has a coefficient of only 1, so we're going to double the second equation. So if we double the second equation, 2 carbon plus 2 O2 goes to 2 CO2. And then the delta H for this, if we double the coefficients, we're going to just double the delta H for that second equation. So that becomes negative 787 kilojoules. And then finally, the last thing we have to do is we see that the last reactant in our chemical equation that we're trying to solve for is H2. H2 only appears in the third equation. It's already a reactant in this third equation. It already has a coefficient of 1. So again, we don't have to modify this third equation. We're going to keep it the same. And then because we kept the equation the same, we don't change the value of delta H at all. It's still that same minus 285.8 kilojoules. So these are the three modified equations that we're going to add together to get our overall chemical equation of 2Cs plus H2 going to C2H2. And if we did our job correctly and make sure we arrange the reactants and products correctly, as long as it's a problem that's able to be solved, you'll be able to then see that the intermediates cancel out, so we don't have to think separately about those. All right, so if we see on our reactant side, what we have is, from equation 1, we have 2 CO2s, but that's going to cancel out with the 2 CO2s that are a product in the second equation, so that becomes, it serves as an intermediate, it's canceled out. We have 2 carbons that don't have any other partner on the product side, so that's not going to cancel. We have H2O, which appears here as a reactant, and in this equation as a product. So H2O cancels out as well. It's a reactant in the first equation and a product in the third, in the rearranged form of those. And then we go down to the rest of the reactants. We have 2 O2s here, another half O2 here. So we have 2.5 O2s on the reactant side that we're going to add together. But if we look at the product side, we also have 5 halves O2, 2.5 O2s there as well. So it cancels out in 2 pieces, but the total O2 that we have on the reactant side, which is 2 plus 1/2, cancels out with the 2 plus 1/2 O2 that we have in this first equation. So things that are on both sides of the arrow we're going to just cancel out. And then the only other reactant that's left is H2, which doesn't cancel with anything. And then on the product side, the only product that's left that hasn't already been canceled out as an intermediate is C2H2. All right? So we can verify that the intermediates cancel out as they should. CO2, water, and O2, which don't appear in our overall equation, should then be canceled out in this way. And then that leaves us with what we want. You have a question? Well, we do care about the quantities. We have to make sure that the coefficients are also equal for those intermediate species. Now, what I'm saying though is if you do it correctly, if you arrange the reactants and products correctly, so remember that the reason that we flipped this first equation was to put C2H2 on the product side, which is where we want it. The reason that we doubled this second equation was to put 2 carbons on the reactant side, which is what we want. And then the reason that we kept this equation the same was to leave 1 H2 on the reactant side. If you do all that correctly, the intermediates will take care of themselves. We're not going to give you a problem that you can't solve. Well, we wouldn't want to do that because we only want a coefficient of 1 in front of H2. So if we multiply this whole thing by 2, we would have 2 H2s instead of 1 H2. We only want to have 1. Other question? Well, it's carbon plus H2. So I'll erase all my marks so you can see it better. So the overall equation is 2 carbons plus H2 going to C2H2. So in this equation, which we're trying to find delta H for, we only want to have 1 C2H2 on the product side. It shouldn't also be on the reactant side, and it should always have a coefficient of 1 if we're going to get the right delta H. Yeah, you don't want that to cancel out. So anything that appears in the chemical equation that we're trying to calculate delta H for, you don't want anything there to cancel out. You just want the species that don't appear to cancel out. So we see that these given equations have O2, CO2, water. All 3 of those should cancel out because they don't appear in the overall chemical equation. And so then once we do that, delta H for this is going to be just the sum of these 3 modified delta H's. So it's going to be 1299.5 plus negative 787 plus negative 285.8. And so the sum of those 3 gives us delta H of positive 226.7 kilojoules. Okay? So this is one of those types of problems that takes some practice to get used to, but we're just trying to figure out a way to add together these 3 equations to get the chemical equation that we're interested in, and then we add together the delta H's to find out what the overall delta H is. But we have to make sure we remember to modify delta H's whenever we change the direction or the coefficients of one of the equations. All right. Let's just do one final example of this before we move on to our next topic. So one more with 3 equations. All right, so we have, in this case, we're forming CO2, so a relatively similar type of equation, formation of carbon dioxide from carbon and oxygen. And we're giving you the following information, which is, admittedly this is the world's most convoluted way to determine the delta H for the formation of CO2, but we're saying we have strontium oxide plus CO2 to make strontium carbonate. We have strontium oxide decomposing into its elements, strontium carbonate decomposing into its elements. So 3 seemingly unrelated chemical equations, but we're going to try to figure out a way to add these 3 together to determine what the delta H is for the formation of CO2 from its elements. Okay? So again, we're going to follow the same approach as we did last time. We're going to focus on the reactants and products in the chemical equation of interest, and we're going to find out where they appear in the chemical equations that were given. Okay? So we see that we have CO2 being formed as a product, 1 CO2, and we see that down here the only place that CO2 appears is in the first equation. Okay? So if we want to form CO2 as a product, but we have it here as a reactant, we have to flip the first equation to get CO2 onto the product side. So we're going to number the equations again, 1, 2, and 3. And for the first one, and again, you don't have to necessarily go in order, but I like to do it just to keep everything straight. We're going to flip the order of equation 1 to put CO2 on the product side, which is where we want it. Alright? So the first equation flips, where the reactants become the products and the products become the reactants. And because we flip the direction of that reaction, we also have to then flip the sign of delta H to become positive 234 kilojoules. Alright, so we're given that the delta H for this is minus 234. If we flip the direction, we have to then flip the sign of delta H. So that's what we do the first equation. We see that for this second equation here, we have O2, which is one of the reactants in our overall equation, but O2 also appears down here. So we don't necessarily want to start with this one. Let's look at reactants and products first. We see that the other reactant is carbon, and carbon only appears in the third equation. Okay? So carbon appears as a product in this third equation, but there's a coefficient of 2 in front of it. So if we want to have just 1 carbon on the reactant side in the equation we're interested in, we have to take that third equation, we have to flip the order of it, and we have to multiply it by 1/2. Alright, so we're going to both invert and we're going to multiply the third equation by 1/2. That's going to get us 1 carbon onto the reactant side, which is where we want it. So we get strontium plus carbon plus 3/2 O2 goes to strontium carbonate plus, that's it, sorry. Alright, so we take this third equation, we flip it, and we multiply it by 1/2. That gives us 1 carbon on the reactant side, which is what we want in the overall equation. And then the delta H for this modified equation is going to be negative 1/2 times delta H for the third equation, because we flipped it and we multiply it by 1/2. So that becomes minus 1220. So we're taking this number, positive 2440. We're flipping the sign because we flipped the order of the reactants and products, and we're multiplying it by 1/2 because we multiplied all the coefficients by 1/2. And then finally we have to figure out, do we even need this second equation, or what do we do with it? Now what we'll notice here is that we have strontium carbonate, which we don't want in our overall equation, does cancel out. We have it as here as a reactant, here as a product. But strontium oxide and strontium are not currently canceled out. So this is where we have to start thinking then about the intermediates in this case and make sure that they cancel out properly. So we want strontium and strontium oxide to cancel out. This chemical equation has strontium oxide as a reactant and strontium as a product, so that's in the right order to be able to cancel out with these two. But the coefficients again are off because this has a coefficient of 2 and we're trying to cancel something that only has a coefficient of 1. So what we're going to do to finish this puzzle is we're going to take this second equation and multiply it by 1/2. So we're going to have strontium oxide going to strontium plus 1/2 O2. And that's going to then allow us to cancel strontium oxide and allow us to cancel SR, strontium, as an intermediate in both cases with the correct coefficients. So because we multiply the coefficients by 1/2, we're going to take 1/2 times the second delta H. So this is the delta H for the second equation, 1184. And we take half of that value to make it 592 kilojoules. Alright, so then when we add together these 3 modified equations, we had to take the inverse of the first equation, We had to take the inverse of the third equation and multiply it by 1/2. We had to multiply the second equation by 1/2. All of those steps are going to then give us our overall chemical equation. So we see that strontium carbonate is a reactant there and a product there, so it cancels out. Strontium is a reactant there and a product there, so it cancels out. Carbon does not cancel with anything we don't want it to, so we have one carbon as a reactant. The next reactant we have is 3/2 O2, but we see that we have 3/2 O2 in this reaction. We have, did I leave something out? I think I'm missing an O2 somewhere, am I? Yeah. There it is. 1/2. And it's, yeah, so that should be 1. Gosh. Spaced out today. Alright, so we have 3/2 O2. It shouldn't cancel out. That's good. It's not supposed to. So we have 3/2 O2 here in the first equation as a reactant. We have 1/2 O2 as a product, so it's going to partially cancel out. A net of 1 O2 on the reactant side. So in this case, O2 appears on both sides of the equation, but because the coefficients aren't the same, it doesn't completely cancel itself out. 3/2 O2 as a reactant, 1/2 as a product. In net, that leaves 1 O2 as a reactant, which is what we want. And then strontium oxide, which is a reactant in this last equation, cancels out up there. And then on the product side, all that's left is this 1/2 O2 already canceled out with the 3/2. We got rid of the coefficient. And then we have just CO2. All right? All right, so as you guys see, I'm not perfect. I thought I was wrong once. And you guys can get that one. So we have, this is the overall chemical equation, and we just have to add up the delta H's. 234, negative 1220 from the second, positive 592 from that last one that we modified, negative 394 kilojoules. Okay, so that's what the final delta H is when we add together these three numbers. So this one's a little bit more tricky, and I sort of messed myself up a little bit because O2 appears in two of the equations, and so we had to figure out how to, basically we didn't want to focus on that one because it appears twice, and we see that if we do everything else correctly, cancel out all the intermediates, O2 will correctly balance out to give us 1 on the reaction side. Alright, so this is something, as I said, you'll have to practice, but we're going to move on to now is something that's very related to this, but a lot simpler in my opinion. So as you can see, there's a lot of really convoluted ways to calculate delta H. This isn't very practical. We took together three equations that have nothing to do with CO2 formation to calculate delta H. So what I'm going to go into now is sort of a more standard way of doing this. And again, the value of this approach is that if we have a bunch of delta H's tabulated for chemical equations, we can just combine those in different ways to find delta H's for new chemical equations that we don't specifically have delta H recorded for, without having to go in the lab and measure it. And the standard way that we do this is not by just picking and choosing random chemical equations, but by using what are called formation equations to do this. So what we're going to get into now is what are called formation equations, which is a more standardized and logical way of doing Hess's law, of using Hess's law to find delta H. You're still going to have to know how to do what we did before, which is adding together equations and adding together sequences like we did. But the way we do it more conventionally is with formation equations. So formation equations are a very specific type of chemical equation where we have, for just about every compound that we've ever studied, we have tabulated data for the delta H for the formation of that compound. So let's get into what all that means. So first we need to define formation equations, and they have a very specific format that we want to be able to recognize. So it's a chemical equation that shows the formation of 1 mole of a compound. So that's a very specific part of it, is that the product side will just have 1 mole of a compound, a coefficient of 1. And what we're forming that from is the elements in their standard states. So we're going to have to spend a little bit of time talking about standard states here in a minute. But that's the definition of formation equation. We're forming 1 mole of a compound from elements in their standard states. And an important thing to realize here is that fractional coefficients are okay and very often are encountered, as we'll see, as long as they're only on the reactant side. You're not always going to have fractional coefficients, but sometimes you will. But if you do have them, they will be on the reactant side. As I said, the product side of a formation equation only has 1 mole of a compound. That's the only thing. So then the general form is going to look like this. On the reactant side, you're going to have some combination of elements. And then on the product side, the only thing you're going to have is 1 mole of a compound. A compound with a coefficient of 1 in front of it. All right, so that's what formation equations look like. It's elements forming a compound. And the coefficients have to be such that you're forming 1 mole of that compound. But the other important point of this is what we refer to as the standard states of the elements. So these elements have to be in what are their standard states, and so let's talk about what that means a little bit. So there's a couple things to know about standard states. First is the state of matter that the element exists in, whether it's a gas, a liquid, or a solid. Most elements on the periodic table are solids, but there are a few that are gases and liquids. So the standard states, the elements that are gases in their standard states are, not surprisingly, the noble gases. So that's that whole last column of the periodic table. All of those exist as gases in their standard states. That said, they don't do a lot of chemistry, so they don't appear in formation equations very often. But they all exist as gases in their standard states. And then there are a few other elements that exist as gases in their standard states, and they're all nonmetals. Not every nonmetal is a gas, but the ones that you should be familiar with are hydrogen. So hopefully these first 3 we already know are gases: hydrogen, nitrogen, and oxygen. And all 3 of these are diatomic in their standard state as well. So that's another important point of it, is that hydrogen in its standard state is not just H, it's H2. It's molecules of H2 that exist naturally. Same with nitrogen and oxygen, N2 and O2. And hopefully those 3 we're already familiar with as being gases. Nitrogen and oxygen make up the vast majority of the air that we breathe. Hydrogen we've all, well, hopefully not played with, but are all familiar with. And then the other 2 elements that are gases in their standard states are 2 of the halogens, the 2 lighter halogens, fluorine and chlorine. All right, and those are also gases. So those 5 elements plus the noble gases all exist as gases in their standard states. These 5 are all diatomic. There are only 2 elements on the entire periodic table that are liquids at standard states. Now, standard states also refers to how they exist at room temperature. I think it's 298 Kelvin. That's not so important for what we're doing, but that's what we define as standard states. How does that element exist at room temperature and at regular atmospheric pressure? But anyway, the only 2 that are liquids under those conditions are going to be the other halogen, or the next halogen, which is bromine, also a diatomic, Br2. And then does anybody know the other element that's a liquid? It's fun to play with, but again, you have to be a little bit careful with it. Mercury, yes. So Hg, which is mercury, is a liquid at standard state. It's the only metal that's a liquid. And then finally, solids are everything else on the periodic table. All right, so there's 118 elements on the periodic table now, and about 10 of those are gases, and 2 of them are liquids. The rest are all solids. The only other ones to be aware of is that there are some solids, specifically in the nonmetals, that also are polyatomic, meaning that they don't exist as individual atoms, but they exist as polyatomic molecules. So the other halogen, I2, is also diatomic. So all the halogens are diatomic, F2, Cl2, Br2, I2. They just have different states of matter. And then the other elements that are polyatomic are phosphorus, which the standard state is P4. And then sulfur and selenium are S8 and Se8. They're octanuclear. Okay, but they're all solids. So those 4 elements are solids, but they exist as polyatomics. So we do need to be a little bit familiar with the steady states for all, the standard states for all the elements, because when we start recognizing formation equations, the reactant side of formation equation should always have an element in its standard state. And if it's not one of these polyatomics that I've listed, the standard state of an element is just going to be that element. So for every metal, the standard state is just the metal. There's no polyatomic metals that we have to worry about. And for some of the nonmetals, that would be true also. All right, so that's what we mean by standard states. And then finally, what we're going to get to then is what's called the standard enthalpy of formation. And this is just simply the enthalpy change that's associated with a formation equation. So every element is going to have an equation that represents its formation, and then the enthalpy change that's associated with that chemical equation is called the standard enthalpy of formation for that compound or element. And the terminology that we often use is heat of formation. So enthalpy of formation, heat of formation mean the same thing. It's the enthalpy change that's associated with a formation equation for a specific compound. And so this is kind of the way, and we'll see how this works in a little bit later, but this is the way that we do it usually for calculating delta H. We don't just take any random set of chemical equations and try to add them together. We take formation equations, we add those together to get the overall chemical equation, and we use these formation enthalpies to allow us to calculate delta H for whatever chemical reaction we're interested in. So the abbreviation for enthalpy of formation is delta H. It has a little F down there to tell you that it's a formation enthalpy, and it has a little knot or degree sign up there to tell you that it's standard enthalpy, which means, again, room temperature, atmospheric pressure. Not terribly important, but that's the abbreviation we use to indicate that it's a standard enthalpy of formation. All right? So let's talk then let's do a quick thought problem. What is the standard enthalpy of formation for an element in its standard state? Is it 0, is it positive, or is it negative, or does it depend on the element? There are a lot of depends. Any other guesses? I've heard just about every answer except the correct one, which is 0. All right, so the standard enthalpy of formation for an element in its standard state would be 0. Think about this for a second. If we form an element, remember, a formation equation has, let's say we're going to form hydrogen, and we're forming hydrogen from the elements in their standard states. We would form hydrogen from hydrogen. There's no net reaction taking place here when an element forms from itself. So that means the enthalpy change has to be 0. Now, if the element was not in its standard state, if we were forming, let's say, liquid hydrogen or something, which is not the standard state of hydrogen, then it would have a non-zero delta H, and it would depend on what process we're doing. But for any element in its standard state, the enthalpy of formation is 0. So there are 118 enthalpies of formation that you guys have to memorize, which is just all the elements. Okay, they're all 0. So the important part about that is that if an element appears in a chemical equation, and you want to use delta H of formation to find the delta H for that reaction, the delta H of formation for any element is going to be 0 as long as the element is in its standard state. All right, so those are the ones that we won't give you specifically. Every other delta H of formation, if you need the value of it, we'll give it to you. There's no way to determine that a priori or to have to try to memorize any of those. That's a foolish exercise. But for elements, we won't give them to you because they're all 0. Okay? So let's then look on to... let's just first identify a formation equation just to see what they look like and make sure that you can identify the features of these. So all of these are chemical equations that involve forming sodium carbonate, Na2CO3, but which of these is actually a standard formation equation? Is it going to be A, B, C, or D? So let's look at these closely. So remember, the two things we want to look for are a formation equation should only have elements on the reactant side. And they have to be in what are called their standard states, as we said. And then on the product side, the only thing we should have is 1 mole of that compound. So these are the two features of a formation equation. We want to figure out which one of these is correct. Formation equation for sodium carbonate. So if we look at choice A here, we see that the reactants are clearly not elements. In a formation equation, the reactants have to be elements. So we can eliminate choice A. These are not elements. In choice B, if we look at it, we have sodium, which is an element, plus carbon, which is an element, plus 3 halves O2. O2 is the standard state of oxygen, and that forms 1 mole of sodium carbonate. So there's a coefficient of 1 here on the product side that's not shown but is implied. And all the reactants are elements. Everything's correctly balanced. Everything's correctly in the standard state. Solid for sodium and carbon, gas for oxygen. And so this one looks like the one that's going to be correct, because it has the correct form for a formation equation. If we look at the other ones, let's see what the problems with these ones are. So choice C, it has all elements and it has a compound on the product side, but we see that the coefficient for the compound is 2. So we don't balance formation equations with smallest whole number coefficients. We balance them with a coefficient of 1 on the product side. So the correct formation equation is going to have a 3 halves O2, and that's okay. This one is going to be incorrect because we're forming 2 moles of compound, so it's not going to be the correct standard form for that equation. All right? All right, so we always balance formation equations with a coefficient of 1 on the product side, and there will sometimes be fractional coefficients, which is okay on the reactant side. And then finally for choice D, what we see is that we have, first part looks good, 2 sodium plus carbon, but we see that oxygen here is listed as 3O. Remember that the standard state for oxygen is O2, diatomic oxygen. So this would not be an element in its standard state, and so that would not be then a formation equation. So oxygen gas is not the standard state. It should be O2. I'll just write this out so you can understand the reasons why choices A, C, and D are not correct formation equations. Choice A does not have elements as reactants. Choice C has 2 moles of compound being formed. It should only be 1. And then choice D has 1 of the reactants in a non-standard state, monoatomic oxygen as opposed to O2. All right, so any questions on identifying formation equations or sort of what they look like? Yes? As long as it's balanced, yes. They can be, so when you have diatomic elements like O2, or if you had, either even higher order ones like P4 or S8, it's going to be, in most cases, required that you have fractional coefficients, and that's fine on the reactant side. All right, so you do have to make sure that it's balanced correctly, but it can be fractional, and it will often be fractional. Other questions? Okay, so that's how we identify formation equations. Now let's see how we use them to calculate delta H. So if we have, let's say we want to calculate delta H for a reaction, and sometimes you'll see again a little bit of a little circle next to it that tells us that it's at standard conditions, but don't worry about the distinctions there. That's not important, as I said. But if we want to calculate delta H when we know delta H of formation for every reactant and product, there's a relatively simple equation that allows us to do this. Now what we're really doing here is Hess's law. We're taking all of the formation equations for the reactants and products, and we're adding them up in the correct way to get the overall chemical equation. But what it then reduces down to is a simple equation in terms of delta H of formation, where we don't have to write down all the individual chemical equations. What we can do is just use those values of delta H to calculate the delta H for the reaction. So what it's going to be is the sum of the coefficients, the delta H of formation of each product multiplied by coefficients, which is, and then we take that and we subtract the sum of the delta H's of formation multiplied by their coefficients for all the reactants. Okay, so it's sum of delta H of formation for all the products minus the sum of the delta H's of formation for all reactants. Remember, as we saw a little bit earlier in this course, this Greek letter sigma tells us that we're summing them all together. We're adding them all together. And then what I'm abbreviating is M and N here are the respective coefficients for each reactant and product. Because as we said, the formation equation is defined for the formation of 1 mole of a compound. And so if that compound has a coefficient other than 1 in the balanced chemical equation, you have to modify the delta H by that amount, by that coefficient, to account for the fact that you're using or forming more than 1 mole of that compound. Okay? So you have to make sure you multiply each delta H of formation by the coefficient before adding them together. And this looks a lot like an equation we saw earlier in the course, remember we talked about using bond energies to calculate delta E, which in reality is delta H. We just hadn't introduced that yet. So we saw that with bond energies, it's reactants minus products. Now we're doing delta H of formation is products minus reactants. It's important that you keep those two straight. The reason for that difference is because of how the different parameters are defined. Bond energy is defined as breaking a bond between two elements. Formation enthalpies are defined as forming the compound in which you're making the bond, so it's kind of the opposite in some sense. So it's going to be products minus reactants whenever we're using delta H of formation to calculate delta H for the reaction. Keep in mind also that any elements that appear in the chemical equation will have a delta H of formation of 0. So really elements will drop out of this formula because they're all 0, but they would still technically be there. Okay, so that's how we use delta H of formation to calculate delta H for a reaction. So let's just look at a few examples of this in practice. And the way this is going to typically be set up is we're going to give you a chemical equation. So the first one I'll talk about is the combustion of methane. So CH4 plus O2 to make CO2 and water. And then we'll give you the delta H of formation for at least some of the reactants and products, maybe not all of them as we said. And we'll ask you to then find delta H for the reaction. Okay? So delta H for the reaction is going to be the sum of the delta H's of formation for products multiplied by their coefficients minus the sum of the delta H's of formation for the reactants modified by their coefficients. All right, so that's the general equation. Then let's look at what we have. So starting on the product side first, we're going to do products minus reactants. We see on the product side we're forming 1 mole of CO2 as a product. So we're going to take 1 times the delta H of formation of CO2. Delta H's of formation are in kilojoules per mole typically. And so you're going to take 1 mole times the delta H of formation of CO2. The other product is water, H2O gas in this case. And so what we want to then do is take 2 times the delta H of formation of water. Because we have 2 moles of water forming, so we need to multiply its delta H of formation by 2 before we add it together. So we're going to take 2 times that. That's the sum of the products. 1 CO2 plus 2 waters with their respective delta H's of formation. And then we're going to subtract that, the sum of the delta H's of formation for the reactants. So on the reactant side we have 1 CH4. So we're going to take its delta H of formation and just multiply it by 1, or just use it as given to us. And then we have 2 moles of O2 as a reactant. So we're going to take the delta H of formation for O2 and multiply it by 2. Now what is the delta H of formation for O2? It's going to be 0 because O2 is an element in its standard state. So this whole term is going to go to 0. We don't have to worry about it. And then the numbers that we'll end up putting in are going to be 1 times the delta H of formation of CO2, which is minus 393.5. 2 times the delta H of formation of water, so 2 times this number here, minus 241.8. Then we're going to subtract from that 1 times the delta H of formation for CH4. So 1 and then CH4 we're given is this one here, minus 74.9. Alright, so we have to be a little bit careful with signs here. We don't want to drop out any negative signs from the delta H values. We're only just going to put a negative sign in front of all of those that are part of the reactants. And so those are the numbers we put in, and it comes out to minus 802.2 kilojoules. Alright, so the combustion of 1 mole of methane releases 802.2 kilojoules of heat, and we determine that by taking the sum of the reactants, delta H of formation, and subtracting the products. Alright, so this is a pretty typical setup for this problem. It's just addition and subtraction, just making sure that we modify the numbers by the correct coefficients and that we put the negative sign in the correct place, products minus reactants. Any questions on that? Yeah, in the back? It should be in kilojoules. I was being a little bit sloppy here, but all of these coefficients are technically in terms of moles. So it's going to be 1 mole times minus 395.5 kilojoules per mole plus 2 moles times minus 241.8 kilojoules per mole. At the end, it's going to be just in kilojoules, and that refers to then the equation written with these specific coefficients. So it would be per 1 mole of CH4, but we don't usually write it like that. All right, but I'm glad that somebody's paying attention to units because it is very important. Hopefully more of you are. Any other questions? Okay, so let's just do one more. We have this reaction which can be used to prepare phosphoric acid. So here we're using what's called red phosphorus, which is just monoatomic phosphorus. So phosphorus plus nitric acid to make water plus phosphoric acid plus NO2. And we want to know what is the delta H for this reaction in kilojoules. So again, it's going to be just products minus reactants. Now one thing we'll notice here is that, remember that the standard form for phosphorus is P4. Here we're using a form of an allotrope of phosphorus that's called red phosphorus, which is just P, which is monoatomic phosphorus. And so you'll see that we're giving here a delta H of formation that's non-zero. So this is an example of an element that's not in its standard state, so we wouldn't want to assume that that's zero in this case. So it'd have to be P4 to be phosphorus in its standard state. So that's one thing to keep our eye on when we do this, is that even though this reactant here is an element, it's the only reactant or product that's an element, but it's not an element in its standard state, so it's going to have a non-zero delta H formation, which we would have to give you. Okay? So the delta H for this reaction then is again going to be sum of the delta H's of formation for the products minus reactants. And we just have to start writing those out. So on the reactant side, we have 1 mole of red phosphorus. Sorry, we're going to do products first. Let's do 1 mole of water times this delta H of formation. So it's going to be products minus reactants, so we'll do products first so we don't mess up the signs. 1 times the delta H of formation of water, we form 1 mole of phosphoric acid, so 1 times the delta H of formation for phosphoric acid. And then we form 5 moles of NO2, nitrous oxide, nitric oxide. So that's going to be 5 times the delta H formation for NO2. All right, so those are all the products we have, and then we subtract then the delta H formation for the reactants. We have 1 mole of red phosphorus, and again, that's going to have a non-zero delta H formation because it's a non-standard element. So 1 times this delta H formation. And then we have as our other reactant 5 nitric acid, so 5 times the delta H formation for nitric acid. And then we just have to start putting the numbers in, so it's going to be, probably going to run out of room, so make it a little bit smaller. Okay, so we have, as products, we have 1 mole of water, and its delta H of formation, I'll write it out a little bit better this time so we can address the question that came up last time. So 1 mole of water, and then its delta H of formation is going to be, we find it up here. It's liquid water, so it's different than the last one we used, which is minus 285.84 kilojoules per mole, probably more precision than we ever need. So 1 mole of water times minus 285.4 kilojoules per mole plus 1 mole of phosphoric acid times its delta H of formation, which is minus 1271.7. And then we have 5 moles of NO2, and its delta H of formation is given as positive 33.2. All right, so again, the easiest way to mess up one of these problems is by messing up a sign. So those are the products, and then we're going to subtract from that the sum of all the reactants. So we have, again, as a reactant, we have 1 mole of phosphorus, red phosphorus, so it's going to be 1 mole times its delta H of formation, which is minus 17.6. And then the last reactant we have is HNO3. We have 5 moles of that. Its delta H of formation is pretty negative, I believe. Where is that number? Minus 173.33. And assuming I didn't transcribe anything incorrectly, and assuming we did the math right in the calculator, we would get minus 507.29 kilojoules. Okay? Which would then, I guess this is multiple choice, that would be choice C. Alright, so it's just a bunch of adding and subtracting. Keeping track of reactants and products and coefficients is important, but not terribly difficult from a mathematical standpoint. Now, I don't have an example like this, but really the only other variation on this type of problem would be if we gave you the delta H for the reaction, you could solve for one unknown delta H formation. So that'd be another slight variation on this problem. It's just doing a little bit of algebra to solve for a delta H formation, but really there's not much more we can do with this by itself. So any questions on using formation enthalpies to calculate delta H? All right, so the last topic in Chapter 7 that I just want to spend a little bit of time on we talked in this chapter a little bit about some of the practical implications of enthalpy. So you might always wonder when you're taking this course, what is the importance or the meaning of all of this? And at sometimes my answer might not be very satisfying. But in the case of enthalpy, I think it's very important because it's a really key concept when we talk about energy and fuels, which especially in the city of Houston is a very big deal, and really everywhere in the world, because you can't do anything without a reliable source of energy. So that's really what the importance of enthalpy is, and especially in fuels. And so let's talk a little bit about the chemistry definition of fuels and sort of how this relates then to enthalpy. So we should have a decent idea of what a fuel is, or certainly we all use them in our everyday lives. So what is its precise definition? It's a substance that has a lot of stored energy. And usually this stored energy is released by burning the fuel. And so what this means is that it's a substance which you can combust, and when you combust this substance, the delta H is very negative. So another way of saying this is that the delta H of combustion is usually a large negative number, which tells you that when you burn this substance, a lot of heat is released. Remember that when you have a negative delta H, that means heat is released to the surroundings. And so when you burn a fuel, you release a lot of heat, and then you use that heat to do something that you're interested in doing. Usually, convert that heat into work primarily, to do, turn an engine or to produce electricity, whatever the case is. Now, another alternative, which is not really important, but just to be complete on this, you've probably heard of fuel cells before. Fuel cells use electricity to release the energy that's stored in fuels, but the more conventional way of doing it is just by burning the fuel in air to release that energy. Okay, so they're substances that have a lot of stored energy, meaning that when you burn them, the delta H is very negative, and you release a lot of energy by burning them. Most of the fuels that we use today are what are called fossil fuels, and so these are formed over millions of years at very high temperatures and pressures, typically, by decomposition of living matter. So when living organisms die over very long processes, the material, primarily the carbon and hydrogen and a little bit of oxygen that made them up, is converted into fuels that are then buried in the ground, and we dig them up and use them for our everyday life. So it takes millions of years to form fossil fuels. That's kind of the key point that we want to emphasize, is that they take a long time to form, and most of the fuels that we use today would be classified as fossil fuels. All right, so in other words, the living matter stored a lot of energy during its metabolic processes. That gets converted into a liquid or solid form when the organism dies, and then we dig that out of the ground. We burn that fuel to then release that stored energy. So there's still a lot of stored energy in these fossil fuels, and they're relatively easy to get because there's a lot of natural sources of them. We don't have to make them ourselves. We can dig them out of the ground or from under the ocean or things like that. So those are fossil fuels. And there's two major types of fossil fuels. So there's petroleum and coal are the two major categories. So petroleum, which we should all be at least vaguely familiar with if you live in Houston, because the petroleum industry is huge here. Petroleum is a liquid fuel, and it's mostly made up of hydrocarbons. So hydrocarbon is a compound that only has carbon and hydrogen. So some ratio of carbon and hydrogen, CxHy, would be the general formula for a hydrocarbon. So petroleum has a lot of different hydrocarbons in it. When you dig petroleum out of the ground, it's going to have a mixture of hydrocarbons. It's not one thing or another. It's a whole huge mixture. We separate those in different ways, and then different components of that mixture we use for different things. The ones that are most useful to us and that make up the majority of petroleums are liquids. And we separate those liquids in different ways. So, one fraction of petroleum would be used as gasoline, one fraction of petroleum is diesel, one fraction is jet fuel, and then there's a whole bunch of other fractions which aren't as valuable for fuels, but we still use them as a lot of the chemical precursors we use to make plastics. So petroleum is very, very valuable both for the fuels that we use for transportation especially, as well as for a lot of chemical products. And so that's what we do. We separate it into, as I said, gasoline, diesel, jet fuel. Those are the three that make the most money for the oil companies. But there's a lot of other important components that come out of petroleum as well. All right, so that's what we mean by petroleum. It's a liquid source. It's an impure source of fuel that we have to separate. And then finally, coal is the other major source. Coal is mostly made up of carbon. It's going to have trace amounts of other elements in it as well. A lot of typically oxygen is a major component of coal, a little bit of sulfur. But it's mostly made up of carbon, and it's a solid fuel. And the different types of coal, depending on where you get it from, depending on what natural source you extract the coal from, are going to have different carbon content. Okay? Now your book has a whole list of I think there's 4 major types of coal that have these geological names that I can never remember. We don't want you to memorize those names, but the principle we want you to recognize is that the higher the carbon percentage in the coal, so these different types of coal differ with respect to how much carbon they have. So if you have a higher carbon percentage, it's going to... Oh, no. That's not good. Please tell me it saved my annotations, or I'm going to be upset. You want me to discard that? You want to see me in an upset state? Now the question is, did it actually restore it properly? It did. So I'll go home happy today. Almost there. Okay. Oh, I lost some of it. All right, I'll have to rewrite those before I post the notes. But that's not a big deal. All right, so what we were talking about then was coal, which is, again, mostly a carbon-based fuel. And as I said, it's a solid. It has variable carbon content, and we don't want you to memorize all the different types of coal, but what we do want you to appreciate is that the importance of this carbon content is that the more carbon you have, which is what I was about to just right before this crashed, the higher the percentage of carbon you have in the coal is going to give you more stored energy. All right, and the way to think about this is when you burn coal, you burn it in oxygen to make ultimately carbon dioxide as the major product. And so coal that already has a lot of oxygen in it has less ability to form carbon-oxygen bonds, or less enthalpy released when you combine it with oxygen. In other words, coal that has a little bit of oxygen in it is already partially burned already, so you don't get as much energy out of it. So the more carbon the coal has, the more stored energy there is, which means the more energy released whenever you burn it. Now, of course, as you may be familiar with, there are some concerns about our continued use and dependence on fossil fuels. So fossil fuels have been around for hundreds of years now in use, but there's some concerns. One of those is greenhouse gases. These are things like water vapor, and then methane. And the big one that comes from fossil fuels when you burn them is CO2. So these are gases that are known to trap heat. So the solar radiation that passes through these is trapped or not able to reflect back into the atmosphere more accurately. And so there's some concerns that these will warm the surface of the Earth. All right, so they trap heat, and there's some concerns then that the surface of the Earth will be kept warmer than it should be, and that if we continue to put more of these greenhouse gases into the atmosphere, especially carbon dioxide, which comes from burning first fossil fuels, the relevant one to what we're talking about today, this may warm the Earth to an unnatural level and cause some environmental and problems and all that. So I don't want to get into all those debates about the implications of this, but suffice it to say there's worries about that aspect of fossil fuels, which is that greenhouse gases are going to cause problems if we keep putting it into the atmosphere. And then another one that's going to show up regardless of what the net effects of greenhouse gases are, whether they end up being awful or just mildly bad or something in between. The long-term viability of fossil fuels is that we're going to likely run out eventually. Now they keep finding new sources of fossil fuels, and so we're not in really any imminent danger of running out. But they won't last forever because, as I said, they take millions of years to replenish. All right, we're using them much faster than they are being formed because, as we said, they take millions of years to form when they're from this decomposing organic matter. And so we can't rely on them just always being there for us. We're going to run out at some point. Now, there's different estimates for when we'll run out. It's probably more on the order of hundreds of years as opposed to decades, but it's still not something that we can take for granted that we're always going to have a lot of availability of. So because of this, there's been a search for alternative forms of energy, and sort of moving into the future, what are we going to end up replacing fossil fuels with? And this drives a lot of research in the area of chemistry. I don't really work on this so much anymore, but a lot of my colleagues do, and I did some work on this as a graduate student. But there's these alternative forms of fuel that are being evaluated as possible solutions for the future, and there's a lot of chemistry research that goes into how do we produce these things efficiently. So one that's being looked at is hydrogen, and the advantage of hydrogen is that it has a very high energy density. And the other nice thing about hydrogen is that when you burn it with oxygen, the only product you make is water. So you don't make CO2. And if you're able to take take the water and convert it back into hydrogen, you have a closed cycle. Hydrogen to water, water back to hydrogen. So that would be sort of an appealing way to do things. Delta H for this is minus 286 kilojoules. So it's a pretty good amount of energy, and hydrogen is very light. So 1 mole of hydrogen only has a mass of 2 grams. So compared to liquid fuels like gasoline, it's much lighter weight than those, so it stores a lot more energy per mass. Now that's the advantage of hydrogen. The disadvantages are that right now it's pretty expensive to produce hydrogen. It would be a lot more expensive to run your car on hydrogen than to run it on gasoline as it currently stands. And because it's an explosive gas, it's difficult to store and transport hydrogen. So liquid fuels are still very much desired. If you've ever heard of the Hindenburg disaster, you'll know one potential concern with hydrogen is how explosive it is as a gas. So there's a lot of also research going into taking hydrogen and converting it into liquid fuels. That's another way that we can do things. And then another major category of alternative energy sources is biofuels. These are fuels, they're typically liquid fuels that are generated from plant matter or that are produced by microorganisms. There's kind of a couple categories of biofuels. Basically, these are fuels that we use living organisms to produce for us. And so because they're produced by living organisms that we can grow a lot faster or that produce these things a lot faster, we don't have to rely on fossil fuels again, which take millions of years. So some examples of biofuels that are currently being evaluated are methanol and ethanol. Ethanol is already used as an additive in a lot of gasoline that you get. I think most gasoline you get these days is about 10% ethanol. And you can use biological organisms to make this, and then another one is called seed oil, which is a plant material that also has a lot of energy content. So I just want to give you a quick overview of sort of the importance of enthalpy in the area of fuels, sort of where fuels are going and potentially in the future. There's some information in the book about that, and probably one or two homework questions will deal with this topic as well. All right, I'll see you guys next week where we'll finish up Chapter 7 and start into Chapter 8.